So my name is John Dykema. I'm a project scientist in the School of Engineering and Applied Sciences at Harvard, and I specialize in atmospheric radiation and its interaction with particulate matter.
I'm Yao-Wei Li from Harvard University School of Engineering and Applied Sciences, and I'm a graduate student. I'm working on the climate and chemistry influence of the aerosols in the stratosphere. So this is our instrument. So it's called the DPOPS, which is a short name of the DCOTSS Optical Particle Counter. So this is one of the two particle instruments on the DCOTSS project. And what we do is we measure a particle size distribution and particle concentration in the stratosphere. So it's a very compact instrument, and we use a laser to shine the laser to the particles, and the light scattered by particles is proportional to the size of the particles. That's how we count and size the particles. So together with the DPOPS instrument, we can get a composition result, the particle size distribution product, which is quite important for the chemistry and climate impacts to assess those impacts of aerosols.
So the range of particles that it measures are particles down to 130 nanometers in diameter and then up to 2.5 microns. So these are quite small particles. When we usually talk about particulate pollution in the lower atmosphere, what we're breathing in, we're usually concerned about things that are 2.5 microns. So that's the small size that we're concerned about for pollution. There's also larger pollution up to 10 microns. So we're really looking at the smaller size particles here, which is well suited for the stratosphere. The stratosphere typically has smaller particles which are either coming from volcanic influence or from industrial and natural biogenic emissions of sulfur. And the thing that's really interesting in this mission is we're also seeing some smoke that is coming from very energetic wildfires and being ventilated into the stratosphere. And in some cases where there are extremely large fires, like there have been in Australia a few years ago, you can have so much of that smoke form or be deposited into the stratosphere that you get, it's like the equivalent of a small volcanic eruption in terms of its climate impact. And there's also concern that it potentially could provide a surface on which you can get free radical ozone chemistry, and you could get kind of a regional small-scale ozone hole due to that fire smoke.
So we will slide this instrument in, and actually the majority part of the work is I will do, so myself will be underneath the nose, and I'll make connections inside. So I just sort of let you know the process.
Yeah.
So, yep.
You can see here there are a number of plumbing fixtures, and those need to be hooked up to different gas supplies, gas inlets that bring in the air from the nose and distribute it to other parts. There's another particle counter that we also feed, and then the air that's coming into the ER2 nose is moving very, very rapidly. And so part of what was challenging with this instrument is to design some custom flow systems which could slow that gas flow down and then pick off particular parts of it, because we only want to sample one particle at a time in here. So as Yao-Wei was saying, we want to shine a laser and get light scattering, and we do that at one particle at a time. And if the particles are too close together, we don't get a clear signal. So we want to have those particles spread out.
I may need your help if you could help hold.
Yeah, absolutely.
And I will make the connection.
Okay.
Mr. Ring. So I will stop here, and I will get